Well, we have been working, and if you recall last time, we finished up chapter 9. Chapter 9 was a very big chapter. If you remember, it had conservation of momentum, which we actually started working on before the test. And then we did everything except for the center of mass, the last part of the chapter, and we did that on Monday after we went over the test. So that's where we were, or we are. So now let's jump into another big chapter. And all that is to say that as you look forward into your next test, your third exam, which would be chapters 9, 10, 11, and 12, 9 and 10 are very large chapters, but 11 and 12 are very short chapters. And so you'll see how it plays out here. And so chapter 10 is a continuation of what we just got done in chapter 9. And I'll start here again. Here's what we had last time at the end of chapter 9. I said, take an object like this, you know, an object that has size, and say, all right, here's the object right here. If I lift it up, what's the increase in potential energy? Yeah, and the whole point of the discussion here was to get to the center of mass, and the idea that if our object now has size to it, parts of it can raise different heights. For example, this part on the end, as it spins around, it rises a much larger height than this one. So how do you treat that? And the idea was, well, there'll be a point called its center of mass, and that's what we need to focus on. So all these rules and all these equations that we learned for the first 9 chapters here can still apply as long as you apply them then to the center of mass. So let's continue on that road of the idea that our object has size and start to look at things. And now look at this issue. Until this chapter, we have not let our objects spin, right? Our objects could not do this. Well, they didn't spin because they didn't have size to them. If they're just a point object, it makes no sense about spinning. And so now they can spin, or what we'll call a rotation. And so this chapter, in the first section, says this. It says, let's look at a rotating object. We'll keep it kind of simple at the beginning here, and we'll say, let's look at the rotation of a rigid object. And also rotate around a fixed axis. And this is the start of chapter 10. So yeah, this is where chapter 10 begins. What I meant to say, 10 begins where 9 left off. 9 for the first time gave a size to our object in the center of mass. Now as we jump into 10, realizing that our objects can have size, they can also now rotate. And so I will start here with a rotating object. And so I've got many objects here that rotate, but here's the simplest thing we can do. You take a wheel and you spin it. Okay? Now look closely at that description. Rotation. All right, that's what we're going to be studying here. So the whole chapter is on rotation. But it says about a rigid object. What does that mean? Rigid object. Yeah, it doesn't change its shape, right? And when you spin it, the wheel has the same radius, if you will. Now, do all objects do that? You ever spin, say, a water balloon? You know, and you kind of watch the thing wobble out here, or maybe a soft squishy ball as you spin it. It changes its shape as it spins. Those problems are much more complicated. So we're not going to do those yet. In fact, we're not even going to do that this semester. In fact, now that I think about it, we're not even going to do that this school, okay? So that, anything that deforms or changes its shape, you'll do after you transfer. All right, so those are much harder problems. And so we got to start somewhere. And so we'll start with making sure all of our objects are rigid. Also, look here. It says about a fixed axis. What does that mean? Yeah, this is the axis. See how the axis doesn't move? Okay? And so this is a rotation of a rigid object around a fixed axis. Now by the end of the chapter, the fixed axis will go away. Okay? The rigid part won't. By the end of the chapter, we'll do this. What happens if this thing is spinning? So we got rotation and it's moving. It's translating. And we should be able to handle that because we've done a lot of translational motion already. And so we're going to see that once we spend the first half of the chapter, or maybe 90% of the chapter, rotating around a fixed axis, the next step is just to put rotation and translations together. And so you'll see that, and you'll see it a lot more in the next chapter. One thing you won't see, though, is our axis changing its direction. So we won't be doing any of this. Okay? Again, that will wait till another school and after you transfer, and so that's a next level up, if you will. A very important one, but like I said, we're going to have a rigid object. We'll start here with a fixed axis. By the end of the chapter, we'll have rotation and translation at the same time, and if we can learn that, that is the goal of this class. And I might point out, not a very easy lessons to learn, but hopefully you will learn them. And hopefully you remember what I did in 102. And I did this in 102. I'm going to repeat it here. I'm going to come over to the sideboard. I'm going to make a little chart. I'm going to cut it into two pieces. And on one piece, I'm going to say, remember all this translational motion stuff that we did. Let's compare that to a rotational motion. And so everything that we've done for translational motion, we are going to repeat. That should make the chapter easy. And so hopefully what you'll see here in this chapter is that even though it is long, if you begin to notice everything we did already, we're just repeating for rotation, I think it'll make the chapter not seem so overwhelming. It won't look like new material to you. It'll be a nice review. And so it is kind of a nice review, especially as we are getting, believe it or not, towards the end. Maybe not that close to the end, so don't panic yet. And we've still, what, got 5 weeks? Yeah, 6 weeks, 5 weeks, something like 6, yeah. So we still got a ways to go, but it's worth this chapter for this just reason. It makes us stop and ponder, what did we do so far? What have we done in the first 9 chapters? And we're going to make a list, and it won't fit here. We'll have to make a second one over here. But we'll repeat everything we've done for translational motion, and then we'll say there is an exact analogy to it when it comes to rotation. And if you see that parallel, it makes the chapter a pretty easy chapter to do. You say, oh, how would I have done this if it was translational motion? And you go, oh, I would use conservation of energy. Okay, so how are you going to do it with rotation? Conservation of energy. Or you look at it and say, well, if it was translational motion, how would I do it? Well, I would have done it with Newton's laws of motion. I would have I would have drawn a free body diagram, and I would have written out Newton's second law. Okay, fine. Do the same thing with rotational motion. So the point here is all these wonderful skills that you have learned for the first 9 chapters, repeat them. Okay? And that's the best way I can explain this chapter. Is if you see the analogy. If you don't see the analogy, this is going to seem like an overwhelming chapter. This is going to seem like we got 9 chapters packed into one. Because it's going to be like, wait a minute, I got all this stuff to learn, energy, momentum, Newton's laws of motion, kinematics, all in one chapter? Yes. Okay? So make sure you see the analogy. All right, so I'll get started here by saying, let's take an object, any object. I'll take an object that maybe is not exactly uniform or symmetric in any way. Now, I don't have one out here like that, but here's my object. Spin it. Okay? And so I take an object and spin it. Let's focus at one point on this object. So in this case, I put some styrofoam spheres in here. Why don't we just look at this one for a moment? And I'll spin that one. Okay? And it will go around in a circle, right? Even if the object, in this case it's a wheel, but what if I were to just, this say is a piece of plywood, and I take a jigsaw and I cut it out, and then maybe right here I drive a nail through it and nail it onto the wall here. And then I say, let's look at some point here, P. And now let's spin this. If you look at point P, what path would it have?
The point of the center.
Would it have a circle? Even though the object, the rigid object, is not a circle? Yes. And that's what I want you to get. If this is a rigid object, fixed axis, it doesn't matter whether the object is a circle or not. The points on the object will make a circle. And so, let's call this distance to the point R the angle from the x-axis theta, exactly like you would have done for any polar coordinate system. Let me draw then the path that this takes, and so there's a dotted line, and so point P would spin around in a circle. And if I looked at just a little bit of the motion, maybe not the whole circle, let's just say we look at a movement, well, I'll tell you what, let's just look at the movement from right here on the x-axis to this point theta there. That's part of an arc, fair enough? And I'll label that with an S, and maybe I should pause. I'm familiar with using S as an arc length. Do you guys do that in your math class? Okay. So let's continue to do that, and your author will too. He calls this S for the arc length. And let me just ask, is there a mathematical connection between R, theta, and S? Yeah. You know what it is? Yeah. S is equal to R theta. Or if I go back a step, theta is R divided by S, right? And so just in case you've forgotten the definition of an angle in radians. Ooh, did you catch that? Let me ask it again. What is the definition of an angle in radians? Right here. It is, what is the arc length divided by its radius? That is the angle in radians. Okay? So don't be surprised if we use radians a lot here, and we will. It has some nice properties. So sometimes we'll use degrees, because it has nice properties. And that's mostly what we've been doing up in this class. But now we're going to start using radians. So one of the warnings I'll give you here as you start to think about, okay, what's the parallel connection between translation and rotation, is instead of measuring position, which we would call this x, and we would use units of meters, what should we do to measure the, quote, position when something is rotating? We will call that theta. And we will use what units? Radians. We're not going to be using degrees, although sometimes we will, so you do have to pause here. But what is the advantage of radians? Well, you'll see that as we work through the chapter, but I'll start with a simple one here. Look closely at this, because maybe you've even heard this statement. Radians are real numbers. What do you mean by that? I mean, how do you know if something is in either radians or degrees? Let's look closely at the definition. What units would you use to measure S, arc length? Meters, right? Or centimeters, you know, some kind of unit of length. Let's call it meters. What unit would you use to measure R? Meters. So what do you get when you go meter divided by meter? Nothing, no units. And that's why we like to say radians are real numbers. They're not really a unit. The only reason we even say radians is because it would sound empty if somebody said, hey, what's the angle? Oh, the angle is pi over 2. Pi over 2 radians. Right? But radians is not really a measurement then. It's more of a clarification. So I'm going to do this. I'll say radians, and maybe I'll even cross it out just to remind you that the radians is only put there for your clarification. So in other words, if I was doing a problem and the problem said cosine of, how would I know if my calculator is supposed to be in radians or degrees mode? Yeah, look at the units. If I had some distance divided by some distance, like S divided by R, aren't I going to get meters divided by meters? What do my units come out to be inside there?
Radians.
Yeah, nothing, which means radians. Exactly. Okay? And so that's kind of my warning here as we get started. There's some real nice advantages of using angles in radians, and we're going to do that in this chapter at times, and at other times we'll be in degrees. And so you have to know how to switch your calculator from radians to degrees, and why you're asked to do radians and when you're asked to do degrees here. And that's the insight that I'm trying to give you, is look at the units here. Okay? All right, so we first see, I think, our first analogy. So our first analogy is this: position. Instead of measuring things in terms of a displacement, a distance, we will measure it in terms of a rotation. What angle does it have? Okay? And we did exactly that first step back in chapter, I guess it was chapter 2. It wasn't really chapter 1. Chapter 1 was, you know, convert kilometers to miles and centimeters to inches. And do you remember how easy that was compared to the test you just took? You've come a long way, right? All right. So, what do we do next? Yeah, we said look at the velocity, didn't we? And how do we define velocity? What do we mean by the velocity of an object? Well, the units were meters per second. Why don't I put that in there? Meters per second. That's the units. But what was the definition, and what was meant by that definition? Yeah, we were saying, what is the rate at which its position changes? How quickly does it change its x position? It goes from, you know, one to another. How quickly does it go from a position, say, of 10 meters to a position of 10.5 meters? Okay, that's the rate of change. So what do you think our first question is going to be when we have an object and it is spinning or rotating around? Yeah, not only at what position is it, but at what rate is it changing its position? And so our first definition here is what we would call then a rotational speed. How quickly is it rotating? How do you think we would define it? Yeah, so you're starting to see the analogy already. Good. And when, like I said, if you see this analogy, this chapter will be short and easy for you. Maybe not short, but easy for you. It'll still look like a lot of stuff here. But what you're really saying is this rotational speed would be defined then as at what rate is its angle changing as it's spinning around. So putting this over in the chart here, I would write this then as a d theta dt. And I'd say exactly that. It's rotational speed. Its rotational speed is a measurement of how is its angle changing. Now, I'll need a symbol for that.
Omega?
Yeah, and if you remember from the 102, we stick to the Greek alphabet. And so the whole idea that the angle was measured in theta and then the angular speed is measured in the omega, we just take the correlation to the Greek alphabet. And so that hopefully helps keep our thoughts straight. Things labeled in the Greek alphabet have to do with rotation. Things that have to do with the translational or linear motion are in the English alphabet. Or is that a fair description? Latin alphabet? What is Latin alphabet? Probably. Anybody know? Latin. Yeah, Latin's probably the best way to describe it, since Spanish and French and I think all, anyways, all Latin-based language. Okay, whatever. But something about that, all Latin-based language. You're asking the wrong person on that one, yeah. We need to ask one of my colleagues there, but Latin is a good way, I think probably the best way to say it. Anyway, so Greek alphabet, Latin alphabet here, okay? And so we will have a parallel going down here in terms of our our description here. Now let's talk about the units. And unfortunately, we are going to have to go kind of quickly here, but hopefully you see that. I mean, I probably don't need to dwell too long on this, I hope, on rotational speed. You have an idea. It's what rate does its speed change? And what would the units be here? Yeah, if I write down the units, I'd say, look, this is measured in radians, this is measured per seconds. You might even say radians isn't even a real number, I mean even in a real unit, so if you want to call it per seconds, I guess you're technically right, but it sounds funny. It just doesn't sound complete when you say, hey, what's the speed of your hard drive? Spinning around there. No, it's 300 per second. 300 what per second? I mean, it just sounds like you're missing something. So we like to say the radians for just that reason. It's 300 radians per second. Well, what do you mean? Well, that'd be a little fast, I think. But 10,000 RPMs, is that what? Some of these hard drives is what? I should try it. 10,000 revolutions per minute. Now, one revolution would be 2 pi radians, and 1 minute would be 60 seconds. Oh yeah, that's 1,050, so 300 is pretty slow. Okay, so 1,050 radians per second would be the angular speed of this hard drive in my computer spinning around here. And so that's our units here. So again, let me put that here, radians per second. Now, what about velocity? Again, going back to chapter 2, was there a difference between speed and velocity? Then what was the difference?
Speed and direction.
Yeah, velocity we used when we talked about its direction. So the speed part was just its magnitude. So does a rotating object have direction? And I think this one might be a little bit harder to see. But I could spin it this way, or I could spin it that way, right? Or it could be spinning on that axis, or that axis, or that axis. So we might call this is a spin around the x-axis. This is a spin around the z-axis. This is a spin around the y-axis. So there is something about direction, and it's a little different and maybe a little bit harder to see. Let me just stick to a fixed axis for a second. When you did your math class, if something rotated this direction, would you call it positive or negative?
Negative.
So something counterclockwise, you call it a positive rotation. What if something was rotating this way? Would you call it a negative rotation, right? So in case you forgot that, let me point that out. You did, and we're going to stick to that tradition. That is the traditional math one. So do you have to stick to the tradition? No, but just like, didn't we have the traditional x-axis positive to the right? Your right, my left. And then we have the negative this way. We're going to do exactly the same thing. If something is spinning this way, let's call it a positive direction. Now remember, since it's rotating, not translating, that word direction, I think, can throw you off. Is there a direction here? Well, more on that in a second, but I see you got a question. Yeah?
Why, when you take the wheel from one hip and it's spinning, and then you put it over your head and put it to the other hip, why is it so difficult when it's up here?
Wondering how much I should answer now or wait till we get it to the end of the chapter, because we're going to answer that, but maybe the answer should be is by maybe I'll do a quick analogy and said, all right, let's say that I had a weight going this way and I wanted to stop it and make it go that way. Don't I have to apply a force to make it go that way? It doesn't just go that way on its own, right? I change the direction of it. Well, that's what you're doing here with this wheel. If this wheel is spinning this way, which direction is it spinning? Positive. And if I do this, which way is it spinning? Negative. I changed its direction. So that's a change in direction, and that's going to take an effort or a force. Technically, the word we'll call it torque. So I'll say more later, but that's the idea, that it's not easy to change it from one rotating direction to another rotating direction. In the same way, it's not easy to stop a car from going one direction and start going the other direction. It takes some effort, some force. So more in a second, and then we'll calculate some numbers on that as we get to the end of this chapter. But back to just this first simple case then, I want to emphasize, is there a direction with this? Yes. And we're going to call that a positive direction. How about this one? Negative. Yes, negative direction. I'll give you two ways to try to remember them. The first one is just use your right hand. Okay? If you take your right hand and you curl your fingers with the rotation of the object, the mass, then your thumb points in a given direction that we can label positive and negative. So watch this. Here's why in your math class you tended to call this a positive rotation. If you took your right hand and you curl your fingers in the direction it's rotating, which way is your thumb pointing? Positive Z direction, right? So we say this thing does have a direction. The direction of rotation is the positive Z direction. So be careful with that one. Am I saying it moves in the positive Z direction? No, this is not translational motion. But yet we still call it a positive Z. And what we mean by that is it's rotating around the Z axis. And it's rotating in such a way that your thumb is pointing in the positive direction. What about that rotation? Same idea. Take your right hand. Curl your fingers in the direction of the mass. Which way is my thumb pointing? Negative Z direction. So that is a negative Z direction. This is a positive Z direction. Okay, that's the labeling we will use. So it's more than just rotational speed. It is rotational velocity. It does have directions. And it will take an effort, as you point out, to take a wheel that is rotating in this direction and now make it rotate in another direction. You have changed the direction of rotation. In the same way, it would take an effort to speed it up or slow it down or change its direction this way. You got to take an effort to do that. You got to take an effort to do that. They both take the same effort to change their direction. I'll give you a second one. If you've worked with mechanical objects, screws or bolts, if this bolt wanted to be tightened, I wanted it to screw into the wall here. Which way do I turn it? Clockwise, right? Somebody said right. Right, I guess, always bothers me. How do you call that to the right? Okay, the top's going to the right, but what's this? Down, what's this? Left, what's this? Up, yeah, so I guess if you calling it to the right helps you, fine, but I've never really understood that righty-tighty thing. It's not righty-tighty, it's clockwise-tighty. I mean, that's the rotation. I mean, it's a clockwise rotation. So this is a clockwise rotation. But if you ever tightened a bolt clockwise, or if you prefer right, it moves the bolt which way? Negative Z direction. Exactly. So we call this rotation negative. The bolt will move which way? Negative Z direction. It's tightening in. And if you move the bolt this way, which way does the bolt move? The bolt undoes itself and moves in a positive Z direction. So whether you want to use your right hand or whether you want to think about tightening or loosening a bolt, both of them help us keep track of how you're going to label this rotation, a positive or a negative. So I'll say it again, it does have direction with it. So we need to kind of keep that in mind. Although, since we're starting off with a fixed axis, just rotate clockwise, rotate counterclockwise, plus and minuses is all we're going to be dealing with here at the beginning. Changing the axis from a z-axis to an x-axis, as I said, will be later on in your education, okay? But at least we'll set the stage that you realize it's not just rotational speed, it's rotational velocity. There is a direction with it. And just like taking a car, and even though it's going at same speed and it changes direction, that takes a force, just like a car going from one speed and stopping takes a force. A wheel is the same thing. You take a wheel, and if it's spinning along one axis and you go to spin it along another axis, that takes an effort. We just call it a torque instead of a force, but it takes an effort. Or if you have a wheel that's already spinning and you go to stop it, that takes an effort. Again, we'll call it a torque instead of a force. But it's exactly the same analogy. You apply a torque force that can make it go faster, slower, or turn. But we won't do turnings because we'll just do fixed axis this semester. Like I said, we'll wait till later, but we want to make sure you're ready for that later stuff. And that's what the discussion is. Well, I'll keep going. What did we do next here in chapter 2 after we had a long discussion about speed? Yeah, we asked the next question. We said, well, at what rate is its speed changing? So speed was the rate at which its position is changing, and acceleration was the rate at which its velocity was changing. Fair enough? And what units did we use? Yeah, meters per second each second, or meters per second squared. And so we said that's a measurement of how does its speed change. Couldn't we do the same thing with the wheel or any other rotating object? Shouldn't we then have a rotational acceleration? And so we will. And so again, starting off by just repeating chapter 2, it gives us a chance to not only review chapter 2, but hopefully get you to see the analogy. And then we'll probably go a little bit faster since we got 9 chapters to do here. We're not trying to do them all today, though. We got 2 days to do 9 chapters. All right, so that makes you feel any better. Okay? But there would be a rotational acceleration. And how would you define it? Exactly. You would say it's the rate at which the speed is changing. So I'd come over here and write d omega dt. Okay? And say, okay, that is the rate of change. And of course, now I would need a symbol for it. What symbol shall I use? Yeah, and you're seeing it, right? We would use, first of all, the Greek alphabet. Instead of the A, it would be the first letter of the Greek alphabet. And so it would be alpha. And so sure enough, we would say alpha for the angular acceleration. And I would have some units here. What units would I be using? Yeah, radians per second each second, or radians per second squared. And so this would be a measurement of how does its speed, radians per second, change each second. If we go back to that hard drive, I know that when I go back to my office after class, my hard drive is going to stop spinning. It was what we say, my computer went to sleep. Okay? Mine said if nobody touches it for 15 minutes, it goes to sleep. And yours probably does too. And what that means is the hard drive stopped spinning. There's no point in having this there spinning there and using electricity if I'm in here. Okay, so my hard drive by now has stopped. But when I go back in there, I'm going to go and first thing I'm going to do is touch the keyboard and I'll hear it go. Okay, and it'll take about a second before it gets up to that speed of 1,050 radians per second. So I would say the acceleration is 1,050 radians per second each second. It took 1 second to change its speed by that much. If this was a jet engine that was rotating, you know, it would have to build up to speed. Or if the plane landed and they shut it off, it would take time for it to come down. And so I think you get the idea. This is probably the easiest ideas that we can do. They were a long time ago, but I also think that by now you guys are very familiar with your kinematics. That was that first test where if things were much simpler than they are now with much more details. They were just position, velocity, acceleration, and time. And so let me pause right there before we leave chapter 2 and go on to other things. Didn't we have a nice set of mathematical relationships between position, velocity, and time for constant acceleration? Maybe I should put those here. So if A is equal to a constant, we worked out a set of equations. Didn't we have what we called equation or kinematics equation number 1? Does that look familiar? So what are we going to have here? Yeah, and if you see the analogy, great. There would still be a type of problems that will show up if you have constant angular acceleration. Now, what if I don't have constant angular acceleration? What am I going to do? Right, the same thing I did back in chapter 2. I would integrate. So in other words, back here in chapter 2, we said velocity was the integral of acceleration with time. When we did that, and we said A was a constant, we got AT plus this constant of integration. We called this constant of integration, after some study, the initial velocity. And that's how we got equation number 1. So notice that if A is a constant, we go to this step. If A is not a constant, well, then we have to know how A is, and we have to actually do the integral, as you did in chapter 2, and as you had on the first test. You had problems like that. So we could do the same thing here. Whoops. We could say, how could you get the angular speed? Well, we would integrate. Now, if alpha is a constant, then we would get omega equals to alpha t plus a constant of integration. And after we study it in the same way we did in chapter 2, we would call that the initial angular speed. And so we would get this equation. And what's really nice about presenting it with an analogy, I don't think I need to do all these integrals, do I? I mean, I don't need to work out all these equations. We did them before. And I probably don't even need to show you how to use the problem. I mean, this would make a great type of problem if it said this, that, okay, the jet engine pulls up to the tarmac and turns off power. Okay? After 80 seconds, the turboprop stops spinning. Oh, and maybe it should say it was initially spinning at 10,000 RPMs. We shut off power. 80 seconds later, it comes to a stop. What is the angular acceleration? And so we've given the initial speed, we've given the final speed, we've given the time to take it, we find the acceleration. And so given any 3 of those 4, we could find the other one, right? And so just like you would have done a problem with translational motion, do it for rotational motion. Well, maybe I'll go real quick, because didn't we have 4 of these that were real nice to use? Do you remember the second one? Good. So what would it be here? Good. So you guys see that, right? In place of x, put theta. In place of v, put omega. And in place of A, put alpha, right? But other than that, everything's exactly the same. And the same type of problems that we were doing for translational motion, we can do for rotation. We would just have things spinning instead of translating there. And so that was our second equation. Remember our third equation? So that was our third equation. And if you remember, we got it by solving the first one for time and putting it into the second one, and we got this. So we really could do the same thing. We could solve this one for time, put it into here, and get final speed squared is equal to initial speed squared plus 2 times alpha times the difference in the angles. Okay? And so again, that's the type of problems we're going to have. We're going to have things like this, things that rotate. And say, okay, how much angle did it rotate given its initial speed and final speed? Or given the fact that it did one rotation, what is its final speed? And maybe I should just ask, see if you're following along here. One rotation would be how many theta? How much theta? Yeah, 2 pi, right? Or in radians. One rotation. So if this was one rotation and I started from rest and I gave you the acceleration, couldn't it say, what is the speed after one rotation? You start here with 0, and if I'm given the angular acceleration, then the difference in the angle is 2 pi, right? How fast is it after 2 rotations? 3 rotations, right? You can put in the angle that it moves, if you will, and then get the final speed. Well, fourth and final equation involving constant was x final minus x initial is equal to initial velocity times final, or plus final velocity divided by 2 multiplied by time. Now again, if you remember this one, we got this one by solving the first one for A and putting it into the second one. So the fourth one was kind of like the third one, except for the third one we solved for time and eliminated time. The fourth one we solved for acceleration and eliminated acceleration. So what would it become over here? Well, final angle minus initial angle would be equal to initial speed plus final speed divided by 2 multiplied by time. And so, again, going kind of quickly because we got 9 chapters here to cover, I think you see how that comes into play. And so what you're going to do on a homework question is, ask yourself, what do you know? And ask yourself first, is this a kinematics type of problem? If the answer is yes, then ask yourself, is it a constant acceleration? Because if the answer is yes to that one, then you can use those 4 equations and take advantage of them. If it's kinematics but not constant, come back here and do the integral, And so that's what we did for translation, so we would do the same thing for rotation. And that's my point. Now, some of you, I think I remember from chapter 2, I suggest, at some point you don't want to memorize all these equations. So some of you memorize just 1 and 2, realizing that 3 and 4 are combinations of 1 and 2, and that's fine. And if you did it there, maybe the idea is to do it here also. Don't memorize 3 and 4. Although often at this point in the semester I have found that we've used this equation so many times that even though students said, I'm not going to memorize that, they end up memorizing it because you've used it so many times by now that you say, okay, well, how could I forget it now? I've used it 17 times, so, it's just programmed into my brain. Point is that everything that we did for kinematics, whether it be a constant acceleration or not back in chapter 2, do it again for rotation, okay? Well, let's keep going with this. And before we even get into other chapters, I want to come back to this picture and maybe clear this part of the board right here and say that we have a kind of an option here. Let's come back to this wheel. As this thing is spinning and I look at those 2 styrofoam spheres in there, which one is going at a faster speed? It's a loaded question. Because isn't the question which one has a bigger translational speed or which one has a bigger rotational speed? What speed are you talking about? It's not a fair question. There's different speeds. There's rotational speeds and translational speeds. And so let's take a moment to look at both. We've been spending this last half hour focusing really on rotational speed. So a number of you said they're the same speed. And I would agree that they're the same rotational speed. But another number of you said, no, the one further out has a bigger speed. And you said that because you were looking at its translational speed. You were looking at how much distance did it travel. And I would agree that this one that's further out travels a greater distance. So both answers are correct, but they're different questions. One is, how do their rotational speeds compare? The other question is, how do their rotation and translational speeds compare? Okay? And so aren't they coupled together? I mean, isn't there a connection between its rotational speed and its translational speed? And so let's take a moment to kind of look at that too before we go any further here. I can come over here and say, let's take advantage of this relationship here. Let me do this. Let me take the derivative with respect to time of both sides of that equation. Over here, I would have ds dt. Over here, I would have the derivative of r times theta. Now, look closely at this one. Particularly look at this one with this word in mind. What are you really saying when you say, let's look at rigid objects? That's why I said we're only going to look at rigid objects. It's going to make our life a lot easier than non-rigid objects. You'll do that later in your education. But what would you say here with a rigid object? R is a constant, right? And so it's nice to have constants when you're taking derivatives, because you can pull them out. Now let's read the math. It's been a while since I said that statement, but make sure as you're doing your physics, you don't just do the math, you read the math. What does this say to me? What does ds dt tell me? Change in arc length with time, right? How would I interpret that? Okay, it's a change in its linear position or translational position. So I would call this its velocity. It's translational velocity, right? How is the arc length changing with time? That's this. Now, granted, I called this an x back here in this chart, but if something's going in a circle, that ds dt is how does its actual length change? How does the arc length change? Because what would I call this? Right, and that's what I was getting after, is you can look at this spinning object, a point on it, and you can say, let's look at its rotational speed or let's look at its translational speed. They got to be mathematically connected. How are they? Well, right here. We just did it. In fact, your author puts a little sub t down here. So I will put a sub t before I put a box around there and say, that's the relationship between its rotational speed and its translational speed. Now, why the sub t?
For translation.
Okay, you call it translational. But another option here is tangential. Because you see this little point is moving across tangential to the circle. If this was not a rigid object, which we won't do, but if it wasn't a rigid object, couldn't it move radially outward? So we might have, in addition to this, a velocity in the radial direction, if it could deform. Ours can't. So what is our velocity in the radial direction? 0. There's no point in talking about it other than it will set us up for the next step, and it will set you up for the future of saying, okay, at some point, especially if you go into mechanical engineering, you're going to have to be spinning objects that aren't rigid, or maybe they appear to be rigid until you really start spinning them, and then there's like, whoa. And the Earth is a good example of that. I mean, we got this big solid rock, and we think, nice rigid object, but what does the Earth really look like? It is very oval. Well, not very oval. That's a little strong, but it is oval because it's spinning, and it has deformed, and it would not be this oval shape if it wasn't spinning. It would collapse back down. So there's our radial direction. So I'll put it here just so that we can make sure we're understanding where we are, especially for the next step, but even more so perhaps for the future where you're objects will change them. So that's what I was saying earlier, and you'll see it again and again. Working with rigid objects is going to be much easier than non-rigid objects. So that's where we start. Rigid objects. Fixed axis, rigid objects. Okay? So whether you want to call this its tangential speed or its translational, I like the translational. That's what it means. Now, with that in mind, let's go back to this wheel. And then we can answer the question, which I think you already did, really. We can say, do all of these, and let me put the third one back in here. It kind of fell out a moment ago. Oh, I guess that's why it's barely stays in there. But do all of these have the same speed? Ah, what speed? You guys are fast, right? All right, so I need to ask, do they have the same rotational speed? Yes. Do they have the same translational speed? No. Which one has the greatest translational speed? Yeah, one with the greater radius. And that's what you see in the math. When R gets bigger, even though they all have the same omega, the ones further out go the faster. And so there's advantages and disadvantages to that. If this is a prop on a boat or a prop on an airplane, what part of the prop goes the fastest? What speed? Okay, so which one has the fastest translational speed? Yeah, it's out here at the tip. And so the tip here is covering a greater distance, it's covering more air, it's giving you more thrust or more push from it than in the other parts of it. So the tip here plays a bigger role than other parts of it. Not to say other parts aren't important. If this was a carousel for little kids going around, which part of the carousel has the greatest translational speed? Translational speed? The horses that are out here, right? And so if you've ever watched the one down here, right? The big kids, and big, you know, the 3-year-olds, they're out here. And the little infants are in here with mommy, you know, and so there's, you know, the difference in the speed. And it's very noticeable when you're on this Ferris wheel or carousel. Ferris wheel too, for that matter. You know, you can really pick up that difference. If this is a spinning hard drive, what part of the hard drive has the largest translational speed? In here. And this is the part that if you were reading or writing memory to, it would go much faster here than here. Well, maybe much faster is a little misleading because there's so many other things involved with writing and reading data, but it would be a little bit faster here than here. That's why your software engineers will program it so that if you save files that you use a lot, they tend to save them over here on tracks 0, 1, 2, and 3. A file that you barely use, they'll store over here and kind of keep track of it so that things will load faster and you know, for the things you use a lot, and kind of keep track and increase the speed there of your computer. Oh, you had to say CD, didn't you? I said hard drive.
No, I'm just asking though. I know you said hard drive, but
Well, because CDs do a little different technology. They have little pits, and the data rate is really about the same. And what the if you listen carefully to a CD, my son has one that he's got this big game on the CD. So it doesn't load the whole game into memory, so the CD's constantly spinning. But when data is getting off of this area, the CD really has kind of a low speed. And the laser, you know, flashes on, off, on, off. When it goes to get data in here, it will actually get it at the same data rate. So what it does is this speeds up. So the angular speed speeds up. And so as the disk reads here, and then here, slows down. It goes here, speeds up. And if you listen, especially like one that was reading a lot of data, you'll hear it go, you know, and you think the thing's going to break. And I know my son's going to break my computer real soon. It's just listening to the different speeds as the CD goes faster and slower. So a little bit different. So the point is the data on a CD all the points have the same translational speed. So to accommodate the different radii, you change the angular speed of it. And so it's a little different. Okay. See a question? All right. Anyways, so this is this whole idea of the speed. Now, we should probably ask this question too. Now that we've asked the question, which one has a greater speed, we can ask the following question, which one has a greater acceleration? What acceleration again, right? Is this a translational acceleration or a rotational acceleration? And I claim you can look at both as this thing is going around here. I claim there's a connection between both of them. And I ask then, what is that connection? And I claim we can get it right from here. I'll start with this and do the same thing. I took the derivative from position to get velocity. If I take the derivative of velocity, I get acceleration. So let's take the derivative with respect to time of the translational speed, and at the same moment we will take the derivative of the other side of the equation. And so this is the derivative of the translational speed. Look closely at this again. What was nice about this is this word rigid. Rigid mean what about R? Pull it out in front, and it is a constant, and you would have that. Now let's do some interpretation to this. What would you call this term here, dv dt? A translational acceleration, or tangential. And this one might be nice to call tangential. You'll see why here, as opposed to translational. But nonetheless, there is a t. And what would you call this? Yeah, and that would be the angular acceleration. So same discussion we had before, except now we're dealing with accelerations instead of velocities, but this would be the mathematical connection. And so again, if we look at their accelerations, and as it's spinning around, as it spins around, do they have the same acceleration? Depending on what time we're talking about. Okay, so let me ask, whoops, about angular acceleration first. And so maybe I'll start here and say, during this time that I'm making it go faster and faster and faster, they all have the same angular acceleration. Do they all have the same tangential or translational acceleration? No, which one has the greatest? Yeah, one with the greatest radius. Again, you see it in the math, it makes sense, because it's also the one with the greatest radius is going to have the greater speed. So it's going to have a greater acceleration in order to have that greater speed. And I'm talking about translational speed and translational acceleration. Now, let me not stop there though, because this is why I mentioned this one. This one, we talked about its radial velocity being 0. It didn't move in and out. So let's talk about the radial acceleration. Do we have a radial acceleration? Now, does it move in and out? No. But does it have a radial acceleration? It does. Isn't that just turning in a circle? I mean, isn't that what we did in chapter 4? Didn't we say that the translational speed squared divided by the radius is the radial acceleration? So, like I said, a big reason I wanted to mention radial velocity here was to make sure that we didn't pass it up when we talked about radial acceleration. Here it's 0, so if we ignored it, we would have been okay. Is this 0? No. So we got to think about that one. So in other words, when an object is going around in a circle like this, and if we have this thing going around at a constant angular speed, what would be the acceleration, either translational or radial? It would be 0, right? In the tangential direction, because it's going the same speed. But does it still have an acceleration? Yes, because it's changing direction. So it does have what we called a radial acceleration back in chapter 4 and chapter 6, when we worked on these. And this was the equation we got. Now let's use this into here, so we can write it as r squared omega squared over r, and this becomes then r omega squared. And so what we come up with is that we do have a radial acceleration. It is not 0. And of course it equals to this, the radius and the angular speed squared. So that's our connections between rotational quantities and translational quantities. Rotational and translational. And so if I come back over to this point P, as this point P is going around, maybe I'll change colors to black, I would say it probably has a tangential acceleration and a radial acceleration. So the next question is, how would I get the total translational acceleration? Don't I have to put the two together? And how would you put the two together? Pythagorean theorem, because I'm adding two components of a vector at right angles. Do you see that in the picture? Okay, and so this is our chapter 3 and 4, right? This is what do we do when we have components to our vector. So just like we did chapter 3 for translational motion, I want you to see chapter 3 here for rotation. We do have components, and so this would come out to be a total like that. In keeping with the theme of chapter 4 where we learn this part of it changes its direction and this part changes its speed, right? And in this case, translational or rotational speed, because they're tied together. So maybe I'll finish this little discussion on acceleration by saying a total then is the translational piece squared and the radial piece squared, and then square root. I have what we would say add them in quadrature. So we don't just add them like 3 plus 4 makes 7. No, no. It's 3 plus 4 make 5. Sounds funny, but right? 3 squared plus 4 squared is 5 squared, right? So 3 and 4 make 5. So we're going to add them. We're going to put them together. It's probably a better way of just describing it. Yeah.
What do you mean by a total?
Well, this is a translational acceleration, but it's not the whole story, because you need an acceleration that makes it go faster and slower, tangential, but you also need an acceleration that makes it turn. And so the total acceleration is the combination of those two.
So it has some direction.
Yeah, yeah. So that's why I think the sub T here sounds better as translational. I mean tangential, so that the total will be the total translational acceleration. Because a total translational acceleration is a component that makes it turn and a component that makes it go either faster or slower. And so we're back to this picture here that we saw again in chapter 4, which I know it's been a while, so it's nice to review that one. But you might remember a problem I did in class about a train as it turned and was slowing down. We had to do its tangential acceleration and its radial and then put them together to get its total. And I think there was a test question that way too. Was there? Yeah, I did one with a train, but I can't remember the test question. Was it a train on the test, or?
It was a train.
A train on the test?
Yeah.
Oh.
Yeah, it was just making a turn.
Okay.
It was slowing down.
Yeah.
Slowing down.
Oh yeah, yeah. Okay. So it was a train on the test too, but it's that same idea. Okay, and again, I really like going through this chapter because it gives us such a chance to review what have we done before, and then let's use that to understand our rotations better. All right, well, let me erase this much of the board so far and say, okay, We've done all this, so I can kind of clean this up. This would be what I would call all the kinematic stuff. And so we've kind of done the repeat of chapters 1, 2, 3, and 4. Mostly, obviously, we focused on chapter 2. I didn't do any unit conversion directly here, but I kind of did. In other words, if I said 1 revolution per second, that would be how many radians per second? 2 pi, right? And so that I did a couple of times here, and that would be the equivalent of chapter 1, converting units, and in this case revolutions to radians, or the other way around, radians to revolutions. I did a lot of chapter 2, obviously. Chapter 2 was the bulk of the material. Chapter 2 is where we talked about position, velocity, and acceleration. Position, velocity, acceleration, and their connection. Chapter 3 and 4 is where we got into vectors and the components, and again, you saw that, right? Well, I erased it now, but right here. And then what did we do? Well, I guess we did Newton's laws, right, in chapters 5 and 6. So we should probably do the equivalent of Newton's laws when it comes to rotation. And we're going to do that, we're just not first. Because then we got into chapter 7 and we did energy, right? And I think energy was a little easier. So let's do energy first. We will do Newton's laws of motion, but energy might have been a little bit easier, so let's do that. And so let's look at the first type of energy here. Let's look at a kinetic energy. I mean, didn't we do kinetic energy before? And what did we say back in, well, I think this was chapter 7, for the formula for kinetic energy? What was it? Yeah, we said, all right, the kinetic energy, we gave it the symbol K, is 1/2 mv squared. Let me put that into our chart. Now, my chart kind of filled up on this side, so let me continue that chart over here. And so over here, I'll put our translational motion here, and I'll put our rotational motion here. I'll put a little line and say, okay, we went through a little integral. Let me not repeat that integral, but we said the kinetic energy of a moving object is just 1/2 mv squared. We didn't give it any size. Of course, now we have, so we would say it would be the velocity of its center of mass, right? That's what I mean by that. It's okay. There would be my velocity of center. What did we use for the unit for kinetic energy? Yeah, we called that a joule. All right, so now let's look at a rotational kinetic energy. Wait, what'd you say? 1/2 what? All right, I'll hold off on the analogy, but good. You guys see the idea that you are guessing, and I haven't even done any work yet, a 1/2, good. You were guessing an omega squared instead of a v squared, good. The place where you kind of ran into troubles is it just an m or does m change? And mass will have a rotational mass, or what we'll call a rotational inertia. And so let me not put all that up at one time. That's too much to do in one step. But let's kind of go through it here. Let's do this. Let's come back to this picture. And so you've noticed this picture's been here, and I'll continue to be here. But let's just say I was looking at this little point P here. Okay? And I said, what is the kinetic energy of that little point P? Forget the rest of it. But certainly, if you wanted to know the total kinetic energy, you would have to do all the pieces here. So I'm just going to put a little box here and say, let's call that little box M. I'll put a little M and then talk about that later. But I would say if I wanted to know the kinetic energy of that one, I would write it as 1/2 mv translational speed squared. Fair enough? And so that would be the kinetic energy. But it's not the kinetic energy of the whole thing. Because let's look at another little chunk. If you took another chunk, maybe this one over here, would that one have kinetic energy? It would, wouldn't it? Would it have the same kinetic energy? No? Probably not. Why not? Okay, different radius means it's traveling at a different speed. And I mean translational speed. So those 2 points on there, those 2 chunks of masses, even if they had the same mass, so if they have the same mass, I would come to the conclusion that as they are spinning, and so this one would make a path that looks like this, that this one here has a lower translational speed than that one. Now, they have the same angular speed, don't they? But they do have different translational speeds. So I wouldn't say they have the same kinetic energy, but I would say this, that if I wanted to know the total kinetic energy, wouldn't I have to add up the kinetic energy of all the little chunks? I mean, I've only showed you 2 so far, but wouldn't I do that for the 3rd and the 4th and the 5th? And so there'd be another little chunk here, and another chunk here, and another chunk, and another chunk, and another chunk, and another chunk, and another. And so that's what I mean by that little summation. Add up the kinetic energies of each piece. In other words, add up the 1/2 mv squared. Now let's work with this a little bit, particularly since they have different v's, don't they? But they have the same omegas. So let's do this. Oh, sorry, I forgot my little summation. So summation of 1/2 m, and could I write this as r omega squared? Now let me put a little better notation on here, because usually when we do a summation, we put a little index here, and we say, all right, if you're going to add up a bunch of pieces, then you need to label those pieces. The first piece, the second piece, the third piece, the fourth piece, and in this case, let's just call it n. So simply put, kinetic energy is going to be a bit more complicated than kinetic energy of the past, because we've got to say, what is the kinetic energy? And we got to add up the kinetic energy of each individual pieces. And so we chop them into different pieces, and we'll chop it into n pieces. Which piece in here would have the most kinetic energy? Yeah, the ones going the fastest, right? The ones going the fastest are the one with the greater radius. So these guys are going pretty fast. So they got a lot of kinetic energy. This guy here, hardly any kinetic energy, right? Barely moving. So that's why the total kinetic energy is a bit more complicated. It's a summation of all the pieces. Now, fortunately, we can simplify that a little bit. Yeah.
Are we assuming a uniform density, so the masses in the center are?
Not yet. No, what I am saying though is whatever the mass is at that point, I would use.
So couldn't they point closer with a smaller radius, but mass?
Okay, yeah, so that, you're right. You're right. That last statement I was assuming uniform density. Yeah, because it could have been a lot of mass at a low speed, and that could have the same kinetic energy as something with a little bit of mass but very fast. Okay, fair enough. But okay, so let me rephrase it. Yeah, with uniform density, these guys would have a lot of kinetic energy, and those guys hardly any. Yeah. Okay. But in general, I don't want to say uniform mass. I do want to come up with a more general relationship. But a uniform one is the easiest one to calculate, as you can imagine. Was there another question? No. Oh, yeah.
So you said that in the center it barely has any kinetic energy. Or is it because we're assuming that it's at a fixed spot only? Because we're not moving it, right? Because it's not moving.
Oh, the axis?
Yeah.
Now, the axis is not translating, but the object is rotating. That's why it has kinetic energy. So let me not use the word not moving. What's not moving is the axis. The axis is fixed, but the object itself is moving. It's rotating. It's not translating. Yeah. All right, well, like I said, the kinetic energy then does become a little more complicated. Fortunately, not too much complicated. Watch this. It does simplify here. What would you say about the omega for every piece? For a rigid object. Yeah, all those are hooked together. So I could simplify this a little bit by saying every term is going to have the same angular speed. Fair enough? And for that matter, every term is going to have a 1/2. It's this other piece, which is the sum of mi/ri squared, that will be different for the different pieces. Because does every piece have the same radius? No. And as you were saying, they may not even have the same masses as we add them together. But if they had, you know, the same uniform density and we took the same size, then they would have the same mass. But even if they didn't have the, even if they did have the same mass, they're definitely going to have the different radii. So it is this piece that goes here, right? See the connection? Doesn't this almost look like this? Doesn't it have the 1/2? Doesn't it have the speed squared? It just doesn't have this. And so that thing is what we are going to call the I. That is what we are going to refer to as the rotational mass. The rotational inertia is the word we like to say. And so as you'll see, it plays the same role as regular inertia. So let's review that. That's why it makes sense to put this line here first and say, okay, what role did mass play? And maybe I should back up. What units did we use for mass? Yeah, when we did translational motion, we used kilograms. And what role did mass play? What do we mean by mass? What do we mean by inertia of something? Resistance to change its, okay, its state of motion, movement, if you will, right? In other words, if something was sitting here and you wanted to get it to move, if it had a lot of mass, it was harder to get it to move than something with a little bit of mass, right? Or the other way around, if it was already moving and you wanted to stop it, something with a lot of mass was hard to stop. So inertia was its resistance to change its state of motion. And it still is that, except now we're talking about its resistance to change its rotation. And this has to do with not only the mass, but the position of the mass. And so this new idea, I think, is one of the hardest ones we see this semester. Trying to get an understanding. It's this and torque that are the two that I even mentioned in 102. I said, I think those are the hardest ones in the 102 mechanics. And I think it's the hardest one here in the 121 mechanics. What do we mean by rotational inertia? Well, again, by analogy, hopefully this helps. What we mean by rotational inertia is the same that we mean from regular inertia. Resistance to change its state of motion. In other words, if I had an object here, and I said this had a lot of rotational inertia, what do I mean by that? Well, I mean it would be hard to get it to rotate. Or if it's already rotating, it would be hard to stop it. But what is different is rotational inertia does not just depend on the mass. What else do you see in that little formula? The R, the position of it. Where is that mass? And so I'll show you with this one, but I think you had a question.
What about gravity? Does that affect the inertia? It's not uniform mass?
Well, all right. I'll say Yes and no to that. I'll start with yeah. I'll start with, none of this discussion so far has done outside forces, whether that be outside force of gravity. So maybe we should say, right now our simple discussion is forget gravity. This is spinning in outer space. Okay? And so just like the space shuttle would be hard to lift because of gravity, forget that. Let's just take the space shuttle out to outer space. It's hard to get it going just because it has mass. Forget the fact that if it has gravity, it just has a lot of mass. Same thing with this wheel. Forget gravity. It would be hard to get it to rotate just because it has inertia. Period. Now, if I now put gravity into the mix, that could make it harder or easier. For example, the space shuttle. If the space shuttle is down on the ground, on Earth, it's hard to lift the space shuttle up for two reasons. Number one, it has inertia, but number two, you've got to overcome the force of gravity. Now, if the space shuttle was already on the top of Half Dome in Yosemite, and you wanted to push it down 4,000 feet, it's pretty easy to push the space shuttle down because gravity is pulling it down. But it still has inertia, okay? So that's a long way of saying there's no difference between what I'm saying now and what we did for translational motion, but what I am saying now has nothing to do with gravity. No outside forces. Just this wheel. If I take that wheel into outer space, it's going to be hard to spin because of its inertia. Now, wheels are kind of easy to forget about gravity because if you look at this, where is the center of mass of this wheel? Yeah, right in the center. And what's connected to the center is metal, an axis. So the structural support of this is pushing up. So, does this wheel fall down? No, why not? Because when it comes to translational motion, gravity is pulling it down, and then the normal force from the table is pushing it up. Those two balance, and it's as if there was no gravity here at all. I just got to worry about the spinning part. So that's why a spinning wheel here, whether it's on Earth or whether it's in outer space, are a lot the same. Because usually the center of mass of a spinning object is at the axis, and you don't have to worry about the effect of gravity. Now that's not always the case. I could have it, you know, center of mass over here somewhere. I could put a bunch of weights here, and then it would rotate kind of funny. It would go fast, slow, fast, slow, fast, slow. And then I would think about that. But right now, that's a long way of saying I'm not even thinking about the force of gravity. And so again, inertia has nothing to do with gravity. Space shuttle is hard to move when it's in outer space, just because it has inertia. So let me see if this little experiment helps. You saw it unwind here a moment ago. Let me wind it back up and say, I'll start with these 4 weights off. And I want you to watch it accelerate. I would say that's a pretty fast acceleration. Fair enough? Watch it again. Take a good look at the rate of acceleration. Because what I want to do is wind it up and put these back on. Do you think it'll have the same rate of acceleration? Why not? What do you think?
There's more inertia.
Okay, I would say it has more rotational inertia. And I would say it has more rotational inertia because it has more mass. And so if you let this go and you watch it, it is a little bit less. Not too much less, but a little bit less, right? Now watch this one here. This is the most important one. What if I leave these same 4 weights here? In other words, I don't change the mass. But what I change is the location of the mass. So have I changed the mass? Have I changed the rotational inertia? Yes. Does it rotate at the same speed? Oh, not even. Much slower, right? And so this has a lot more rotational inertia. Okay? So again, what I'm trying to get across here is this analogy. We had inertia which resisted its change of motion. We have that again. We have rotational inertia. But rotational inertia is more complicated, which can make it more interesting. which I guess is a way of thinking if a teacher says it's more interesting, it probably means it's more complicated and the problems are harder because more things can happen. And that's what we have here. We have two things happening. You can change the rotational inertia either by A, changing its mass, but that one's so obvious it probably doesn't need to even be said. But the second one is not so obvious. Couldn't you change the rotational inertia by changing the position? And that's what this last one was about, to show you that as I move the weights outward, I get a different rotational inertia. And in this case, it's a bigger one. And you saw the effect of a bigger rotational inertia. It does not accelerate quite as much. And so I'll say it again. I think this is one of the hardest things we do all semester. Really trying to understand what do we mean by rotational inertia. And if it helps, it's the same as inertia, except it has position and mass. And that makes the calculations and the understanding a little bit hard. It also brings us back to here. Did you understand what inertia was? You didn't confuse inertia with weight. And that's always a tough one to get to at this level. Inertia and weight are not the same thing. Weight is a force. Inertia is a resistance. You have inertia when you're in outer space. It's hard to move the space shuttle when you're in outer space. No, it might even be harder when you're on the surface of the Earth because you got to move the inertia of it and you got to overcome the force of gravity. Yeah.
What's the application M for the sigma?
Oh, that would be the summation of how many pieces did I chop it into. So if, let's say I cut this into 10,000 pieces, this means you add up the first, the second, the third, the fourth, the fifth, the sixth, the seventh, until you get to 10,000. Okay? So, in my picture, my N would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 so far. 15, 16, 17, 18, right? So I got to add up every piece. So sometimes we just do this, sum of the I, meaning add up all the pieces. And we don't specify how many did you chop it into. So I don't know, which is less confusing for you? That? Or the other way?
No.
Yeah. So that's just how many pieces am I chopping it into. Did I chop it into 10 pieces? 100 pieces? And I think you can see that the more pieces you cut it into, doesn't it become more accurate? Because when you take a piece here, isn't part of it a little closer in radius than a little bit further out? So I haven't gotten this far, but I'm eventually going to do this. Chop it from 1 to infinity. Let's cut it into an infinite number of pieces. So that means you have to add up an infinite number. And how do you do that? Hey, you're getting it. You integrate, exactly. That's that big lesson. Is could you come up with your integral equation all on your own? And we've done it 3 times. This will be the last and final time before we kind of finish for this semester and say, okay, remember it, because you're going to need to do that a lot next class when we get into electricity and magnetism. I thought I saw another hand. No? Oh, yeah.
I was just going to ask, if you only want to find the inertia of a single point, would you still use a summation or just center of mass?
Well, technically, you would need to chop any size object into an infinite number of pieces. But sometimes our pieces are so small that we say, it's close enough to a point. And that's my first example I want to do for you. If I was taking this object that we saw in the chapter 9 and I said, let's spin it. Could I calculate the rotational inertia of these two objects? And if you remember from last lecture, we calculated its center of mass. And we said this object was 3 times the mass of that one. Okay? And this distance is 1/4 of the whole length. You remember doing that? And so now we can spin it and say, okay, how does this thing spin? And I'm going to just do 2 objects. I'm going to say object 1 and object 2. But in reality, can you see how this object, these points here are actually a little closer than those? So if I take the center of it, I'm making a little mistake because the center only works for linear functions. Isn't that r squared? So it's not as easy as just taking the center of mass. I wish it was. Oh, I wish it was, because then we can just say, hey, you got a big complicated object, just find its center of mass. And then you would only have to know how to calculate center of masses. You wouldn't have to know this calculation too. But I'm trying to give you a warning is, you can't just do center of mass for this. So you got to do center of mass for the stuff we learned about in chapter 9, and now you got to do a different calculation for the stuff I'm showing you in this chapter.
So you have to get the kinetic energy of the big one and the small one?
So let me show you by examples here. And I think to answer your question is, if I just took the kinetic energy of the center of mass of this one and added it to the kinetic energy of that one, it wouldn't be quite right, because these points on this side of the sphere are traveling faster than these points. And the fact that you're doing the middle doesn't mean you've completely compensated for these guys in here going slower compared to these guys going faster, because the center of mass did a linear operation, but moment of inertia and kinetic energy needs a quadratic operation. And so these points out here have a disproportionately amount more kinetic energy than these points here. And right there, that means our calculus is going to be so critical here and so important that we can't do the same center of mass calculations. So center of mass is great. Center of mass is great if I say, hey, pick this up and tell me what the new potential energy is. But if it's rotating, don't try to say the kinetic energy of that thing rotating right now is the same as if it was all at a point at its center of mass. That's what I'm trying to say. It's not that simple. I wish it was. I wish there was a lot of things in physics that were much simpler. It'd be a lot easier to teach, a lot easier to learn. But that's just not the way it is. And we don't make the rules, we just learn the rules. And that's, you know, we can blame Mother Nature for all that. But Mother Nature made it complicated. So we got to figure that out here. All right, so let's kind of look at this, but really this calculation first, because like I said, that calculation I think is one of the tougher ones, and the concept one of the tougher ones of the semester. So what I've said so far is that rotational inertia, which we'll use the symbol I, has the same type of properties as regular inertia. It resists its change of motion. It's part of the kinetic energy, okay? But in order to do it, you got to remember that rotational inertia is more complicated. It's not only m for mass, but it's also r for distance, right? So let's take this object, and now that I had that long discussion, let me overly simplify it. Let's say this whole thing is just at a point, and this whole thing is at a point. So they don't really have size. We'll give size back to them. But if this was just two objects without any size, could you calculate the rotational inertia of that one? So let me put it on the board here. Let's see. I'm going to rotate it around its center. This one over here has a mass of 3m and is a distance of 1/4 L. The other one is at a distance of 3/4 L and has a mass of m. And I'll put a little dotted line and maybe even put a little oval with an arrowhead there, kind of showing it spinning in a circle. So here's my contraption. Spinning at a circle, again, overly simplified. Haven't given this ball any size. That will soon change, but and probably not today. But we will give this ball size. But for right now, just to get our first understanding of it, can you calculate the rotational inertia of this? So I would do this. Rotational inertia I equals a summation from 1 to 2. If that helps, that's what the capital N is. The capital N is how many pieces do you have? In this case, I have 2. I'm going to add 2 of them together. And so it will be an MIRI squared. So in this case, it would be the mass of the first one times the radius of the first one squared, plus the mass of the second one times the radius of the second one squared, right? And now I would put it in. So the first one is 3m. Its distance is 1/4 L squared. The second one is 1m, and it's 3/4 of L squared. So 1/4 squared is 16, and a 3 makes 3/16 ml squared. This one over here makes 9/16 ml squared. A 3 and a 9 make a 12/16, and a 12/16 reduces to 3/4 ml squared, right? So there would be the rotational inertia of that object. Overly simplified, not giving any size to this, but illustrating the first step is you add up the number of pieces. Okay, if you have 2 pieces, add 2. You have 3 pieces, add 3. You have 4 pieces, add 4. Okay, and so this would be the moment of inertia. Maybe I should ask about the units. So far I've avoided that question. But what are the units here? Yeah, that would be in kilograms, and that would be in meters. So putting that into our chart, that looks very different than anything we've seen so far. That's kilograms and meters squared. So the units for rotational inertia are more complicated, as they should be, because the whole calculation for a moment of inertia is more complicated. It's mass and distance. It's both of those. Okay. Now, let's use that up here to talk about the units for rotational kinetic energy. What would that be? Well, let's start with I. I would be kilogram meters squared, as we just mentioned. What would angular speed be? Yeah, radians per second squared. What does that simplify to? Right? What do we say about a radian? It's really a nothing. How about we drop it away? Then what do we have? Joules. Okay, so hopefully it doesn't surprise you, since we're talking about the kinetic energy, that it comes out to be joules. But I wanted to convince you, it does come out to be joules. And also show you an example of where it might be wise just to drop radians. It would make less sense to leave radians in there. So sometimes it's useful to leave radians in there. Sometimes it's useful to throw it out. It's not a real unit. It's a clarification. So here I'm going to throw it out because it doesn't help me. It makes things worse here. So my rotational kinetic energy should be labeled in joules in the same way translational kinetic energy is labeled in joules. Rotational inertia, though, is not labeled in kilograms, which it shouldn't be, because it has to do with more than just mass. It does have kilograms in it, but it also has distance, and it has distance squared in it. Right? Okay. I'm guessing that if I change this problem and put a third object out here, maybe a half a L, and said it had 2m. Could you find the rotational inertia of that one? Well, maybe I better do it. All right. In other words, I showed you which, the simplest case I could show you 2 objects. So what would I do with 3 objects? I would just add 3 of them. So I would say I equals summation of I equals 1 to 3 of MI/RI squared. And so in this case, I would be adding 3 objects. The first one would be a 3m at a quarter of L. The second one is my m at 3/4 of an L again. So that's the same first two. But now this third one that I throw in there has a mass of 2m and is at a distance of 1/4 L. And so this breaks down again to be a 3/16 ml squared. This comes out to be a 9/16 ml squared. And then this one is a 1/4, and then times 2 is a 1/2. Let me write it as 8/16 m over L squared, so that I have an m over L squared, I have a 16, but now when I put the 9 in the 3 and get the 12, I put the 8 to it and I get the 20, which, depending on how you want to reduce it, is 5/4 if we leave it as an improper fraction. Maybe I will, and just leave it as an improper fraction. And so that would be the inertia now. How about a fourth object? Could you do it?
Sure.
Fifth? Sixth? How about an infinite number?
Yeah.
So,
Would it be with respect to if we did?
let's take this rod. What if I were to take this rod, drill a small hole in here, and spin it about its center? Could you tell me the rotational inertia of this rod? Let's give it a try. What does it come out to be? So let's do problems like this, except we're going to cut it into an infinite number of pieces. And so here's the picture. The rod looks something like this. I'll drill a hole in the center. I'll put a little circle around that, and I'll spin it. Let's call the length of the rod L. Let's say the whole rod has a mass m. And just to make this one as simple as we can, let's just say it has the same density all the way through. So it's just a piece of aluminum that we poured in. So it's got the same 2.7 grams per cubic centimeter of aluminum all the way through. So same density all the way through. Simple problem, right? Certain length, certain mass. The simplest continuous problem I can give you. The simplest problems are these. Add up 3 or 4 or 5 or 6 objects. But now, what am I going to do to calculate the rotational inertia here? And let's do it conceptually first. I'll change colors to help you visualize it. But what if I just took a small little piece here and called that little piece MI? Okay. How would I get the rotational inertia of just that one little piece? Well, I guess that one little piece, which I will call I sub I, would be MI RI, right, squared. What would R be in that little picture? Wouldn't this then be the R? So you weren't thinking L, were you? You weren't thinking L over 2, were you? And so if you then say, well, how am I going to get the total? Wouldn't you sum it of all those pieces? And when I say all those pieces, I've only drawn one up there. But there would be another one here, and another one here, and another one here, and another one here. And let me just not put them so close together that it looks like one big blue piece there. But I think you get the idea that I would have to chop this into how many pieces? 10? 20? Infinite number. And so I am saying take a summation from I going 1 to infinity of MI RI squared. In other words, we are taking a summation and we are taking so many pieces, something is going to 0, and hence we're going to have an integral. Okay? Did you catch that? That's how I create my own formula and call it an integral. I start with a summation and realize the whole point of Newton's little symbol, in case you didn't catch this in your calculus class, why does he draw it like that? S for sum. Yeah. It is a summation. It is a Riemann sum, is what you probably did somewhere in your calculus as you were doing your pre-calculus and getting you exposed. You were going through the same logic that Newton went through as he was developing calculus. And now you can see why he developed calculus. He was trying to do all these crazy problems, and nobody had done it before. Nobody had taken a rod and chopped it into an infinite number of pieces. And he wanted to know, could you do that? Could you chop it into an infinite number of pieces? Whereas most people in his day, and maybe you yourself, are going, I don't have enough time to add up an infinite number of pieces. I just can't do that. And fortunately, you can do it. It doesn't take an infinite amount of time to add up an infinite number of pieces. Okay? It becomes an integral. All right, so help me out here, because unfortunately, this is the part of the calculus that I think is the hardest in this class, because unlike your calculus class just gave you an integral and said, gave you the problem and say, here's an integral problem, do it. You know, do the integral of the inverse tangent of the natural log of e to the x. Okay. Fortunately, our integrals won't be that hard, but what will be hard is, how do you know it's supposed to be an integral? How do you come up with the equation yourself? So, help me out here. What is going to 0? All right, I'll start with all those answers. Is r going to 0? No, r, as I chop this up into smaller pieces, doesn't this little blue piece get smaller and smaller? It's not that the distance of that blue piece gets smaller. So no, r is not getting smaller. What is getting smaller is the mass. Now, I heard somebody else say a delta r, and I probably understand what you're saying. You're saying the size of this object is getting smaller, and I agree with that. But the size of the object is not in this equation. There's only two things in this equation, either the m or the r. Which is it? One is going to 0 if this is going to become an integral. And to set it up right, you got to decide which one is going to 0. And the fact that the m goes to 0, except for last chapter, you probably do that in your calculus class. You did things like x goes to 0. But I'll say it like I said last chapter. Remember in your calculus class, when you let x go to 0, you really didn't mean x as position. You meant x as a variable. Anything you want to put in x's place goes to 0. So in this case, that's m. We're letting m go to 0. But of course, in your mind, you're thinking, well, wait a minute. If m goes to 0, when I go to add this up, I'm going to be adding from one position of space to another position of space. So there's got to be more to this integral, because the way it stands right now is not solvable. I mean, what would this come out to be? How would you write this on the board? Okay, so there's an integral. Well, let's not worry about the limits yet. I'll ask that. But what goes right here? Yeah, it's the dm that I was interested in. This is the part that goes to 0. So it's important in your concept, as you look at the physical picture here, that you realize what is going to 0. And what is going to 0 is the mass. That's the part that becomes the dm. It's no different than when you learned your calculus, you wrote it as the sum of f of x dx, where the limit as delta x goes to 0 became an integral of f of x dx, right? There's the small thing going to 0. There's the small thing going to 0. Okay? Exactly the same logic, except don't call it an x, call it an m. Now, that runs into troubles because you're saying, now what are my limits? Whoa. If you... Yeah, and your first reaction unfortunately, is going to get you into troubles. I mean, you are saying, I'm going to add from over here to over here, right? So you're thinking about adding over space. But right now, we have an addition over mass. So probably the next thing is to change the dm into a dx. And then it'll look much nicer to you, right? Then you're going to say, hey, let's add from this point to here, to here, to here, to here, to here, to here, to here. So I would love to change this from a dm to a dx. And in this case, I mean x as in space. I do not mean x as a variable like in your math class that can stand for anything. I mean literally x. What is the position? So, how am I going to change a dm into a dx? And we did this very quickly at the end of Monday's lecture. What do we do? What was the magical trick? Yeah, we mentioned density. So let me put the little symbol rho for density. What's the definition of density? Okay, mass per volume. But since we're just talking about a one-dimensional rod, can I just call it mass per length? All right, so I'm going to call this mass per length. And so just like we did at the end of Monday's lecture, if I were to look at the density of this little tiny blue piece, its mass would be dm. That's what I meant here, right? The mass of that little blue piece is my dm. And how long is that little blue piece? Well, let's call that dx. And so dx is what somebody said earlier is probably a delta r, saying, look, let's look at the size of that object. So what you're really saying is that this ratio remains a constant. That is, as you make the thing smaller and smaller and smaller, the density doesn't change. If you make it smaller, you have less mass, but you also have less distance. And so you get that same ratio. But what it helps us mathematically is if we solve this equation, it says dm then is equal to rho dx. And that's going to be very helpful here. So I can write this as r squared equals then to a rho dx. And so this is that change of variable. Change it from my physical parameter where I came up with my own equation dm and convert it then into an integral over something that kind of makes sense to me, a dx. For those of you who might be further along in your math, when you do a variable change like this from a dm to a dx, you can change the dm to a dx and there's some multiplication factor, usually called the Jacobian if you want a big fancy word there. And so here's your Jacobian. Anybody do that? Where do you do that? 200. Is that 200 where they go into details about, oh, it's the derivative of the derivative in the little matrix, and okay. And I don't want to use the big fancy word only because I think it just makes it harder. I don't want you to think it's some with a matrix from our 200 or even that you need math 200. I can just get it from the geometry. That's my point. I've got everything from geometry. And what you will see here is we're going to have a very easy integral once we finally get to the integral. So the actual doing the integral is usually not what's hard in this class. What's hard is these first couple of steps. Is how do I know I was supposed to get an integral? Well, because I'm taking the sum of an infinite number of things. What things go into zero, so I know what to call a dm. And once the little piece. And once I know the little piece, how do I convert it to something that is over space so I can actually set limits here? Because when you get to this part, it now becomes pretty easy. Now you're adding over space. So where would you start and where would you end? Yeah, I would go from negative L over 2 to positive L over 2, depending on where you put your origin. But I'm going to put my origin right there. That's what it's spinning around. So if it's spinning around there, I would say I'm going to add the little blue pieces that are here, which are at negative L over 2, and then I add them up until I get to a positive L over 2. And so that's what I think many of you were looking at the limit before. But you wouldn't want to put it here because you really don't have a sum over space yet. So once we've done this step, then we can do this step. Now it's going to be pretty easy, except maybe I need to make one more step. What's r in this case? Do you see that? What's R? Okay, it's not L over 2. L over 2 is, of course, this radius spinning around. But coming back up to here, what did R mean here? What was the whole meaning of this? And I'll take this as a moment of saying, again, more than ever before, read the math. For this to work, you got to understand what is going on with the math. I said it a lot of times at the beginning of the semester. Yeah, you got to read it. If all you do is plug and chug, you do okay. And all the stuff we did before, you can get away with plug and chug a lot more than anything we're going to do from here on forward. Here, you got to understand what each step really means. And this is a good illustration of that. I got an integral, I changed a dm to a dx, all from reading the math. Not necessarily doing the math, but understanding the concept of what is each step along the way. And I see this again when it comes to r. So I ask again, what did r mean back here? Because it hasn't changed here. And so what did it mean here? Distance of that corresponding mass. So it's not L over 2. L over 2 is only this corresponding mass. The R is here, and it changes for each individual chunk of mass. So it is a variable that changes. And what would it be with a coordinate system where this is the origin? X. It's really that simple. So the hard part is not doing this integral. Can you do an integral of x squared? Piece of cake, right? Do that blindfolded. Right? That's not the hard one. The hard one, did you see r was supposed to be an x in this case? Did you see the dm was supposed to go to 0? Did you see that the summation was supposed to be an integral? Did you see how we could convert a dm into a dx? That's all of the reading of the math. Because now it's going to be a piece of cake. All right, I'll finish the problem. I don't want to erase that, although, yeah, I might as well. We're pretty much out of time. We'll do the rest of this on Monday here, but now I'll do this integral. What do I get? Well, the first thing I'm going to do is just pull the density out and pause and say, well, why can't I do that? It's constant. Is every problem going to be a constant? Oh, no. So don't pull it out every single time, okay? But in this simplest case, which may not look very simple anymore, density did not change. But you have a problem there where it changes. It goes from being aluminum on this end to being brass on this end. And there's a continuous change along the way, and brass has a higher density than the aluminum, and so you've got to figure out how does the density change there. So watch that. But in this case, it does not change. So then I've got density. What's this integral? X cubed over 3 evaluated from minus L over 2 to plus L over 2. So if I put density, and I'll even put the 3 here, this would become L over 2 cubed minus a negative L over 2 cubed. Simplifying this a little bit more, this 2 cubed is an 8, this L cubed is L cubed. And these are the same thing. Once you take the negative cubed and another negative, so there's 2 of those, right? So this 2 cancels with the 8, and you have 1/12 rho r cubed. And I could probably do one more step that's worthwhile. Let's look closer at density. What was density again? Mass per length. Now, early on, I did a little bit of mass over a little bit of length. But wouldn't that also be the same as all the mass over all the length? If it's uniform density? So, before I finish the problem, let me put that back into here and write it as all the mass over all the length. And I get 1/12 ml squared. So there's what I was looking for. What is the rotational inertia of this rod spinning about its center? 1/12 ml squared. See the units? M for mass, L for length. The 1/12 you probably would have never guessed. I don't think there's any way to guess 1/12. You got to do the integral to come out with the 1/12. Now we're going to run out of time, or we are out of time here, but let me ask you this. Very important understanding. If I were to change this problem, which we will on Monday, and say let's not spin it around its center, let's spin it around its end point, would I get the same number here? 1/12 ml squared? No. So when I get this number, I need to be very clear. This is the moment of inertia of a rod about its center. Because if I'm not about its center, do I get the same number? And what if I don't have a rod anymore? What if I now have a disc? Do I get the same number? Well, if I spin it this way, and my point is that we are going to look at this, we get different numbers for different physically shaped objects. And we get different numbers when they rotate around different points. So, a lot more to talk about. All right, so good luck.